Alrighty. Okie dokie. So, last time in calculus class, all right, we talked about finding antiderivatives, all right, which is kind of like going backwards from what we've been doing, right? We've been differentiating, and yesterday we talked about antidifferentiating, going backwards, right? Finding the original function for a given derivative, all right? And we talked about how when we integrate, right, that as we came to know it as being called also integration, we realized that when you integrate here, there's really an infinite number of solutions. Okay, there's an infinite number of functions whose derivative yields 2x. Okay, when we integrate this, we end up with x squared, right? The derivative of x squared gives us 2x, but really x squared plus any constant, when you take its derivative, will result in that 2x there. So we want to make sure that we not only kind of integrate this thing, but also add that plus c in there, because we can always have a constant that's just kind of tacked onto the end, because when we take a derivative of a constant, it becomes 0 and it goes away. So kind of a new idea there with that. All right. And so let's see. I want to see if there's anything else important to hit here. We learned about the new kind of notation too. Okay. All right. Let me actually back up. That solution with the plus c, it's called a general solution. Okay. To the differential equation here, we kind of had a differential equation because we started with f prime, and we wanted to then find the original function f. So this is a differential equation. It's an equation with a derivative in it and stuff like that. Okay. Getting the plus c there, it's the general solution. We have the notation here. We use this symbol. That's kind of like our operation symbol for integration, right? We integrate something, so it's integrate f of x, and we get the capital F of x there. Okay. Let's see, what else? Of course, like the derivative and the integral are by nature kind of like they're inverses of each other. Okay, so when you integrate a derivative, you get the original function. Okay, and when you take the derivative of an integral of a function, you still get the original function there. Okay. They cancel each other out. Okay. We came up with a general power rule here, where if we integrate something to the n power, x to the n power there, then it becomes x to the n plus 1 over n plus 1 plus c, or you can do 1 over n plus 1 times x to the n plus 1 plus c, however you want to describe it there. Okay, we did some examples, right? Then we went through all of our, some of our major derivative rules. We skipped some, right? We didn't touch like the inverse trig, anything like those. And then, over here, we came up with kind of their magic integral rules. Again, these are the rules that you are responsible for now, up to this point. Okay, you need to know these. Okay, you need to know them. Okay, so. And then finally, we did some rewriting, some integrating, and then some simplifying here. Okay, I left off 2, so I'm going to quickly run through those, and then we'll also finish up this example 5, and then we'll finally jump into what we're going to do today. Okay, so. To rewrite our integral here to a more helpful format, all right, cube root of p, we can rewrite it as p to the what power? To the 1/3. So we'll say p to the 1/3 times p minus 4 dp. Okay, and then what should we probably do at this point before we integrate here? Simplify, we'll distribute, right? Yeah, we're going to distribute to the two terms there. Okay, and so we end up with p to the 4/3 minus 4p to the 1/3, again, dp. Okay, bless you. Okay, so now we can integrate. We're going to add 1 to our exponent here. So 1 plus 4/3, 7/3 over 7/3, right? Minus 4p to the, okay, so we have to add 1 to this exponent too. So 1/3 plus 1, 4/3, bless you, over 4/3, bless you again, plus c. Okay, and so I don't like having fractions and then fractions, so we'll finish off here by saying that's going to be 3/7 p to the 7/3 minus 3/4 p to the 4/3 plus c. Okay?
Wouldn't it be 3p 1/3?
Oh, I'm sorry. There was a 4 in front in the initial part there. My apologies. Yes. So it would just be 3. I missed that. Missed the 4. Yes. 4 divided by 4/3 would just give you 3. Okay, thank you for that. All right, next one here. All right. Is there any sort of rewriting that we should do here?
Yes.
Yeah, okay, so what do we need to rewrite? 2 over theta, right. So we'll say that's going to be the integral of secant squared of theta plus 2 theta to the negative 1 plus cosecant squared of theta d theta. Okay, notice I didn't take the integral. We could have integrated secant squared and cosecant squared right off the bat, but I didn't do that. You could have here. I just didn't. All right. So anyway, the integral of secant squared, tangent of theta, very good. Okay. So 2 times theta to the negative 1. Okay. So we're going to add 1 to our exponent here. No. What's the integral of theta to the negative 1, or 2 over theta? What is that? Natural log. Yeah. So 2 natural log of the absolute value of theta. Okay. Remember back to our rules over here, right? The integral of 1 over x, or in this case we had 1 over theta, right, is the same thing as the natural log of the absolute value of theta, or x, right? When we have that x to the negative 1, when we have that x to the negative 1 there, okay, we might say, oh, that's the power rule, but if we do it, we get x to the 0 over 0, okay? If you see this, you're making a mistake and you need to go to the natural log, okay? So, like, it's okay to make this mistake as long as you catch yourself and realize, no, this is not right. I go to here. This should never be an answer that you get from integrating. Okay, you should never end up with x to the 0 over 0 upon integrating. Okay, should not happen. So please make sure you catch yourself and make sure it's natural log of x. Okay, hopefully this would send off, like, warnings in your head and stuff like that. All right, that something's up. All right. So anyway, you go back to this. All right, and then what's the integral of cosecant squared? Okay, it'll be negative secant, or negative cotangent. Negative cotangent. Okay, of theta. Okay, because the derivative cotangent is negative cosecant squared. So if you have positive cosecant squared, we need a negative cotangent. Of course, then plus c. Okay, and so there's our solution there. All right. Questions on any of those? Yes, Sean. Yes, go for it. Any other questions? Okay, moving on. Let's catch up then to number 5 as well. I kind of talked through number 5 yesterday, but we'll go ahead and do it real quick too. Okay, we're asked to find the particular solution, y equal to f of x. So in other words, we want to find the original function given the second derivative. Okay, so given the second derivative and we want to find the original function, what should we do with this second derivative? We want to integrate and find that first derivative here. So we will integrate sine of x plus 2 with respect to x. Okay, please don't forget to write the dx there too. Okay. And this will be f prime of x is going to equal that. Okay. What is the integral of sine? Good, negative cosine of x. And the integral of 2x. And then don't forget your plus c there. At the end. Okay. And so we now have f prime of x equals negative cosine of x plus 2x plus c. Okay? At this point, we have that c value that shows up. We could integrate from here. We could, but we maybe want to try and figure out what that c value is. Okay? What piece of information can we use here to find our c value? The slope of f of x, which is really talking about then what? F prime at 0 is 3. So that means f prime, when x is 0, is 3. So that means we'll put a 3 here, and we'll plug 0 in for our x's. Okay. What is the cosine of 0? Ooh. It'll be 1. Cosine of 0 is 1, so negative 1 plus c, okay, and so c is 4, okay, so f prime of x, the particular solution here, right, we have the general solution, the particular solution for this situation with this information is negative cosine x plus 2x plus 4. Okay, but we're not done yet, right? Because we want to find f of x. So what should we do from this point? Integrate again. Okay, so that's f of x equals that, whatever it is. Okay. So the integral of negative cosine would be negative sine. Okay. Integral of 2x, well, it's x to the 1, so we're going to add 1 to our exponent here. So it'll be 2x to the 2 over 2. Plus 4x, and then plus another c. This is a different c value than the previous c value, right? This is a c. This is the particular the constant of integration for f, not f prime now. So it's different c. All right, so we can simplify this here. We get f of x equals negative sine x plus x squared plus 4x plus c. Okay. And let's see here. How can we figure out our c in this case? What's going to go in for x? Pi. And what's going to go over here for f? 1. Yeah, so it's 1 equals negative sine of pi plus pi squared, plus 4 times pi plus c. Okay. What is the sign of pi? 0, and negative 0 is still 0. And so we have pi squared and 4 pi, so I'm going to just subtract both those quantities over. So we'll have 1 minus pi squared minus 4 pi equals c. Kind of a strange constant there, but it is a constant, right? Pi is a number, so pi squared will still be a number, 4 pi will still be a number, so it's just some weird constant. And so our final answer here, f of x equals negative sine x plus x squared plus 4x plus 1 minus pi squared plus, well, we'll do plus minus 4 pi, plus negative 4 pi. So I kind of committed myself there to the addition sign. Okay? So there it is, final answer for f of x. Okay? And that is all your constant, that's all of a constant right there. That's the c. Okay? Questions on any of that? Easy peasy, hopefully. All right, so again, this thing is called the particular solution because we find a precise value for c there. We found a precise value for c. All right, so let's go into some application. Right, back to our good old friends, position, velocity, acceleration. All right, so a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Okay, that's not a lot of information, but all right. And so remember, to go from position to velocity to acceleration, what are we supposed to use? The derivative, or we will differentiate, right? Take the derivative. So from position, velocity to acceleration, we want to differentiate. So if we want to go from acceleration to velocity to position, what should we do? Integrate, exactly right. We're going to use the inverse. So that is how we will be using integration in these problems, right? We're going to be using it to go backwards. All right, so letter A asks us to find the position function, giving the height s as a function of time t. All right, and we're going to start, okay, by kind of like using the, the kind of typical assumption here that on Earth, okay, acceleration due to gravity, okay, is considered to be a constant negative 32 feet per second squared. Hopefully I didn't offend any physicists in here by doing feet per second squared. Or negative 9.8 meters per second squared. There, much better, right? Oh, don't use that feet stuff in here. Well, we have to use the feet stuff though, right? Because our units are in feet. Okay, so we're going to have to use the acceleration equals negative 32. Sorry. All right, so acceleration equals negative 32. Right? If it's a constant acceleration, it does not depend on its time. The acceleration for an object, due to gravity is just negative 32, we'll say. Okay. So then, given the acceleration, how do we proceed to find position? What should be our first step? Integrate. And if we integrate this, we will get the what? Velocity. So yes, we're going to integrate here. Equals the integral of negative 32 dt. Okay. And what is the integral of negative 32? With respect to t, it'll be negative 32 t, because we're using t with respect to t here, plus c, of course. Question?
Do we have to write the step where you said the integral of a of t?
No. I just chose to do it because, just for the notes, you know, just so you guys can have that, yeah. Because you can see it there. Okay? We're interested in position, but before we can find position, we maybe need to come up with this, what this constant of integration is. What do we know about the velocity of our this particular object here? Do we know anything? 64 feet per second. Okay, so that means we can set this velocity, 64, equal to that negative 32 t plus c. But what's the time when it hits 64? Yeah, initial velocity means t equals 0. Okay, initial velocity t equals 0. So you can plug 0 in for t here. Okay. I'm going to write that here. Initial velocity t equals 0 equals 64. Okay, so I'm just going to use that right here. Okay, so c is 64. Okay, so then we have v of t equals negative 32t plus 64. Okay, there it is. And then, are we done? What do we need to do now? Integrate again. Okay, so we'll say, I'm going to run out of space. I'll do it over here. S of t is equal to the integral of v of t dt. And so we will integrate negative 32t plus 64 with respect to t again. Okay, t, remember that's t to the 1. So we're going to add 1 to our exponent. It becomes t squared. So we negative 32 t squared divided by the new power, 2. Right, and then 64 becomes 64t. Of course, you can talk about dividing by the new power of 1, but it doesn't really matter. And then we have another c. Another constant integration shows up. Okay. Are we done at this point? Can we stop here and say this is our answer? What do we still need to do? Find c, right? Okay, find c. So what do we know about our position of our object? Initial height, that's a position, is 80. So that means the position is 80 at what time?
0.
Yeah, so initial height equals 80 at t equals 0. So we'll say 80 equals negative 16 times 0 squared plus 64 times 0 plus c. It's nice when you have the initial quantities because all those t's are 0, so it just cancels out and gives you c as 80. There's no solving to be done. And so you get s of t finally, after all that fun math, is 80. Of course, those of you guys that are familiar with physics and stuff like that, you have a formula that you guys use or something to determine the position of an object. Okay, so and you see well there it is, right? There's our v naught. There's our initial position right there and stuff like that. So we've seen this formula before, but now we've kind of derived it, I guess. We came up with it on our own. So anyway, there it is. Okay, there's our position as a function s of time t, a function of time t. Okay, questions on that? Pretty easy. All right, letter B. What is the speed of the ball when it hits the ground? Okay, so blast from the past here. Speed. How do you find the speed of an object? Is it just the velocity?
No, you want speed and acceleration.
Don't need to. So the speed. I see what you're saying. So we consider the speed is changing, increasing or decreasing. That is considering both velocity and acceleration. But if we're just trying to find the speed, so if we're trying to find if the speed's increasing or decreasing, yes, we need to know both velocity and acceleration. The speed is increasing if the velocity and acceleration are the same sign, right? Both are positive, both are negative. The speed is decreasing if they're opposite signs, if velocity is positive and acceleration is negative, or vice versa. But if we want to know just the speed, what do we want to look at? Not the position, not the acceleration. It's velocity. But it's not just the velocity. It's the absolute value of the velocity. Remember that the velocity can be both positive and negative, right? You can be talking about going a positive, kind of like 32 feet per second or whatever, but a negative 32 feet per second. What does the positive and negative in velocity mean? What does it tell you? The direction, right? For speed, there is no direction. There is no direction. It's just the speed, right? If you're driving 35 miles per hour forwards, okay, we say your speed is 35 miles per hour. If you're driving 35 miles per hour backwards, we say that you're driving very dangerously, but it's still your speed is 35 miles per hour, right? So velocity, however, would be positive 35 miles per hour forward, negative 35 miles per hour if you're driving backwards. Okay, right? So what is the speed of the ball when it hits the ground? We want to find the velocity. Ooh, when does the ball hit the ground? When the position is 0. So we got to set the position equal to 0 first. Okay, so the position equal to 0 first. Okay, I think we can factor out a 16 here, right? Yeah, so we get 0 equals, I'm going to factor out a negative 16, just so I don't have a negative t squared. Minus 4, minus 5. Okay, and so we want to factor t squared minus 4t minus 5. Hello? Yes, you may. Bye. Okay. So, you Madison. I was like, I have two Madisons. They didn't specify which one, so one of you. Oh, okay. I know, you're just so enthralled by the calculus. I mean, how could you? There you go. Gotcha. All right, so anyway, we'll factor. Okay, and so let's see here, minus 5 plus 1. And so we get t equals 5 and t equals negative 1. Okay, and of course, which t value are we interested in using here? 5, right? We really want to talk about going back in time. Okay, so 5. So we're going to use that t equals 5 and plug it into the velocity. So now we're going to take v of 5. Okay, and let's see here. That was negative 32 times 5 plus 64. Okay, right. I really shouldn't be doing this, but oh well. Equals negative 96. So the answer is negative 96 feet per second. No, Mr. Widmeyer. The answer is 96 feet per second is the speed. Okay, remember that speed equals the absolute value of velocity. Okay, absolute value of velocity. Okay, so 96 feet per second. Okay, question?
So we chose the t-value of 5 because the negative, we don't use the negative value.
Yeah, no, it wouldn't really make sense in the context, I think, talking about like going backwards in time and stuff like that.
I guess I just got confused because you were like talking about absolute value, so I assumed that it was like plus or minus 1. So we would just use the plus.
Well, what are we taking the absolute value of, though? Not the absolute value of t. We're taking the absolute value of the velocity is the speed. So, yeah, that's why. Okay? I'm going to put the absolute value symbols in there. Okay? Letter C. After how many seconds after launch is the ball back at its initial height? So, we're trying to solve for a what value? T, because we want to say how many seconds, so a t value there. T equals what, right? After launch is the ball back at its initial height. So what is the ball's initial height? 82? 80 feet. 80. So we want to set 80 equal to what? The position. Yeah, 80 equals the position. So 80 equals negative 16t squared plus 64t plus 80. And so then we say then 0 equals, I'll go ahead and factor out a negative 16 here again. Actually, I'll factor out a negative 16t. And so I'll have with t minus 4 there. So again, subtract 80 from both sides, you get 0. Factor out a negative 16t then from what's going to be left over here, and you're left with that. And so we get negative 16t equals 0. We get t minus 4 equals 0. So you get t equals 0. That's the initial height, right? The time t equals 0, our height is 80. That's where we get that time from. But then later, the ball is going to be coming back down, bless you, and that t equals 4. So at t equals 4 seconds, the ball will be back at that initial height as it's returning now to the ground. Okay? So 4 seconds there. All right, questions on any of that? All right, moving on then. Let's take a look at number 7. Particle starting at the origin moves along the x-axis, and its no apostrophe. Its velocity is modeled by the equation v of t equals 6t squared minus 30t plus 24, where t is in seconds and v of t is meters per second. How is the velocity changing at any time t? Be sure to include units of measure. What thing describes how the velocity is changing? The acceleration. How do we find the acceleration if we're given the velocity? Derivative. Ooh, we know how to do that. Okay, don't forget how to take the derivative now that we started integrating, right? We have to kind of like go back to our old, kind of rules. We're probably more comfortable with it at this point, though, so be careful. Okay, there it is. What would be the, and this is kind of weird here, I guess, but what would be the units? Meters per second squared. Okay. It's kind of, we don't have a specific number there, but that quantity would be any acceleration would be in meters per second squared. Okay, because we were told the velocity is meters per second, so then the acceleration would be meters per second squared. Okay, letter B. What is the particle's speed at 3 seconds? What should we do with that 3? Plug it into the velocity. Okay, so v of 3 equals 6 times 3 squared minus 30 times 3 plus 24. Okay, so let's see here. We'll have 9 times 6, that's going to be 54 minus 90 plus 24. Yes, okay, so let's see here. 54, take away 96, 30, negative 36, and then plus 24 will be negative 12. Did I do that right? Okay, and so our answer is negative 12. No. No, it's not. What's the answer? Positive 12, because the speed is the absolute value of the velocity. So 12 meters per second. Okay? Okay, speed equals the absolute value. Okay, so please be careful with that. Okay, and of course, when you do problems like this, the authors of the problem will never make sure that the velocity at that particular point is going to be positive, so that way you're guaranteed to get it right, even if you forget that the absolute value is the speed is the absolute value of velocity. Of course, they will always make sure that the velocity is negative at that point, so that if you don't remember that speed is the absolute value, you'll get the problem wrong, right? Okay, so please, please, please make sure that you do take the absolute value here. All right, letter C. What is the particle's position when the acceleration is 6 meters per second squared? Okay. So we want to find the particle's position, but first we have to figure out when. That means we're solving for a t. The acceleration is 6 meters per second squared. What's the acceleration of this thing? Well, we have from earlier, right? 12t minus 30. So 12t minus 30, we want to set that equal to the acceleration of 6. So t will be 3. Okay, right? Add 30, get 36. Divide both sides by 12, you get 3. Okay, we've got the time when the acceleration is 6 meters per second squared. Now we're supposed to plug this into what? Position. Do we have a position function? How can we come up with a position function? Integrate the velocity. Okay. So I'm going to use s of t. You can say x of t here. You know, there's kind of two typical ways, either s of t or x of t. I'll use s of t here. Equals the integral of 6t squared minus 30t plus 24. Okay. So integrate that here. Let's see, that's going to become t cubed. So it's going to be 6t cubed over 3 minus 30t squared over 2 plus 24t plus c. I forgot the dt here. So we can simplify this. So 6 over 3 is 2t cubed minus 15t squared plus 24t plus c. And now if we plug in 3, we're going to have a problem. What's our problem going to be when we go ahead and plug in 3 here? Well, so we're going to try and find the position, right? We're trying to, what is the particle's position? So we want to find that y value when t is 3. But what's the problem? We have this c value that's going to be hanging around, and we want to come up with a number here. So we need to come up with some sort of information about our position. Does it say anything about position right here? No, we do not know anything about our position in this part. But we are told some information about the position of our particle. What do we know?
It says it starts at the origin.
Aha! A particle starting at the origin. That little throwaway phrase there that we maybe like just kind of glossed over, that is important. Starting at the origin means that at time t equals 0, the position at 0 is what? 0. Okay? So we're going to say 0 equals, and then 2 times 0 cubed minus 15 times 0 squared plus 24 times 0 plus c. So c is what?
0.
0. I'm running out of space here, so I'll just keep going. So we have, so s of t for this particular problem, right, our particular solution, 2t cubed minus 15t squared plus 24t. Okay, so we finally got the position, so we're done, right? No. Now what do we have to do? Plug in 3. Okay, at this point, if it's a free response question, do we need to proceed any further? No. The only thing I'm going to suggest you do, though, is like maybe put like parentheses around the whole quantity here and say, meters. Right? Make sure you give it units because of our scenario there, but it is in meters. Okay, so it's not necessary to solve there. But you do, I think, -9 is what you get. Okay, I just typed that in the calculator there, just for sake of speed. Okay. But again, remember, if it's just arithmetic, you may stop and say that many meters. Okay. All right. When is the particle changing directions? What do we look at to determine when the particle is changing directions? What tells us a direction of motion for the particle? Velocity. Velocity. Velocity is all we got to look at for the changing of directions. So we'll look at the velocity. How can we determine when the particle, though, is changing directions? Set what equal to 0? Velocity. Yeah, set velocity equal to 0. Okay. We can factor out 6 here. All right. So 6, I'll have t squared minus 5t plus 4. And so that does factor to be t minus 4, t minus 1. And so you get t is 4 and t equals 1. Okay? And so can we go ahead and then say the particle is changing directions at t equals 4 and t equals 1? Yeah, no. What do we still need to take a look at? Not the acceleration. We got to check that little number line here and see what's happening, what's our velocity's sign, SIGN, whether the velocity is positive or negative in these intervals, right? Because, for example, at 1, if velocity is positive on this side and positive on this side, is the particle changing directions at 1? It wouldn't be, right? If it was positive here, the velocity would not be changing directions, okay? So we have to check to make sure that we are, in fact, changing our signs, okay? So we're going to do this, all right? So let's see here. We'll plug in 0, so we're going to get a positive 24 for our derivative there, so that's positive. Between 1 and 4, let's pick 2. Okay, 6 is positive, so that's not going to be a problem. 2 minus 4 is negative. 2 minus 1 is positive, so positive times a negative times a positive, negative. And then beyond 4, we can say like 5. 5 minus 4 is positive. 5 minus 1 is positive. 6 is positive, so positive, positive, positive is positive. So when is the particle changing directions? 1 and 4. Okay, and again, I'm going to say label them here. Please make sure you label. Okay. There's no justification, but if you were asked to justify, it's simply just saying the particle changes directions at t equals 1 and t equals 4 seconds because the velocity changes from positive to negative or negative to positive at those points. Okay, that's all. Okay. When is the particle furthest to the left? What topic or what concept is this asking us to find? So furthest to the left is talking about the what of the particle? Position, okay? We want the furthest left. Remember that in this case, right, we're describing a particle moving along the x-axis, okay? So that's why we got that whole idea of moving furthest to the left, okay? So position describes where it is on the x-axis. We want to know when the particle is furthest to the left. That means, what are we trying to find here? Absolute minimum. Furthest, absolute, to the left, minimum. Okay, so this is absolute minimum, okay, of position. That's what that's asking for. Okay. How do we find the absolute extrema of something? What do we consider?
Critical point.
Critical points. Do we know the critical points? It's when the derivative is 0 or does not exist. Aha, we have those from earlier, right? There's the derivative equals 0 right there. It does not exist. Well, the derivative never does not exist, right? So that's not a problem. Anything else we got to consider besides critical points? Endpoints to interval. Do we have an interval here? No, not really. I mean, I guess technically 0 might be like our left endpoint there. Okay, so maybe we should consider 0. Okay, but otherwise we'll try. We'll go from there. So let's try. So then, how do we check to see if they're absolute or not? What do we plug those into? The original, the position, the thing we're trying to. So we'll say S of 0 here. We'll say S of 1, and we'll say S of 4. Okay. Okay. Well, we know the initial position. It's 0, right? We were told that at 0 it's 0. And then we'll try these other ones here. Let's see. We have so it'll be 2 times 1 cubed minus 15 times 1 squared plus 4 times 1. And then for 4, it's 2 times 4 cubed minus 15 times 4 squared plus 24 times 4. Okay, I think I plugged those in correctly here. All right. Yeah, okay. So 2 times 1 cubed will be 2, minus 15 plus 24. So 2 minus 15, negative 13 plus 24 will be 11. Okay. And then let's see here. 2 times 4 cubed. So 4 times 4 is 16, 64, but times 2 is 128. 4 squared is 16 times 15. Yeah, 240. Okay. And then let's see, 24 times 4, 48, and then 96. Okay, so 128 minus 240 plus 96. I think we can at least kind of agree here that we're going to end up with a negative number, right? But let's take a look. Oops, plus 128 minus 240 plus 96. Okay, negative 16. Okay. So when is the particle furthest to the left? T equals 4. Okay, seconds. So there it is. T equals 4. Okay, absolute minimum. Okay. One more here. Oh, question. That's okay.
With the number line, couldn't you have also solved it there when it was decreasing and increasing? Couldn't you just said it?
So good point. Good point. Okay, so let's talk about that real quick here. So if we think back to our number line, as Gabe is kind of indicating to us here, if we look, right, we have indicating here that v, the velocity, is positive between 0 and 1, which means the position will be increasing between 0 and 1. Then the position will be decreasing from 1 to 4. Then the position will be increasing from 4 to infinity. Right? Okay. So here's the catch, though, right? So can 1, let me talk about this. 1 is what type of relative extrema? A relative maximum. Can a relative maximum ever be an absolute minimum? No, it's impossible. Okay. By definition, relative maximum, it's at the peak of like a hill there or whatever. You're going to have values to the left and to the right that are lower than it. So there's no way that it can ever be an absolute minimum. So we can throw 1 kind of like out right away. The problem is, though, between 0 and 4, again, if we're considering 0, and I don't know if we necessarily need to consider 0 here, maybe only one to consider 4, but the problem is that 0, we increase, right? The position is increasing between 0 and 1, and so like 0 will be smaller than 1, and then we decrease from 1 to 4, so like the question is, the increase that we did from 0 to 1, how does that compare to the decrease that we do from 1 to 4? And we can't quite tell enough there from that, so we need to do that extra analysis because we just don't have enough information right here. So we need to at least plug in 0 and 4. We don't need to check 1, though, at least. So does that make some sense there? So, okay, but certainly 4 is a good candidate because it is a relative minimum. Could it be an absolute minimum? Possibly. All right, moving on here. Okay. So why don't you guys go ahead and give this next one here a try. Number 8, a missile is accelerating at a rate of 4t meters per second squared from a position at rest. Velocity is 0, in other words, in a silo 750 meters below the ground. How long will it take the missile to reach ground level? Okay, so why don't you guys go ahead and give that a try. Okay, give it a try there. And I'll come around and help maybe if necessary. I am. Cheater, pumpkin eater.
It does not say calculator.
It does not, you're right. It doesn't say calculator inactive.
Alright guys, quit.
What's that? Okay, great stuff. Okay, so you have this C out, right? What do you know about velocity? Velocity is 0, so at time t equals 0 when you're starting, right? Because it's this is looking at it as from a position at rest, velocity is 0. So I guess I would say time t equals 0. What'd you get? Yes. Good job. So in this case, velocity is 0.
I took so many.
Let me guess.
I like to show my work. Can I go get a drink of water?
Yes.
Well,
So like, you don't need to write like that in of that, so you want to do anything there, you integrate it so you don't need to have the sign anymore. Yes. Yes.
And then like
C0. So it's your velocity is just 2t squared. What is it? Plus 0.
okay, and then I have to do one more time.
Yeah. That's position. Really in position.
No, but C equals then.
So this is your answer right here. See, no, that's it. No, that is right. Yeah, that's right. When you simplify it, it'll be that. Of course, make sure what you do is second. So, what do we get? You were told velocity is 0, but this is accelerating at the rate of that. So the acceleration relation the missile is at ground level. So it means you want to find the you need a position. So if you have acceleration, 2 windows away, or pick one way to do.
And the primary
Twice. If you pick one, the velocity is plus c.
Plus c.
you're doing it fantastic.
Well, let's see, there's a window and another window. Well, then just use the door. And then just do whatever.
The door is right there.
It's not a hypothetical, I'm talking about this room.
Okay, number 8. Hopefully you guys got about 10.4 seconds, okay? Questions on any of that? Questions on any of that? Of course, maybe a better answer would be the cube root of 1,125 because that's also correct, right? And it's fine to leave it that way. Okay, it's precise. Here we're rounding. Okay, remember it's okay to round. That actually ends up being the correct rounded answer too, 10.400, right? If you have to round it there. Yeah. Okay. Questions on that? We're all good? We got one more here we're going to look at. The motion of a bear stalking its prey. Walking left and right of a fixed point. Can be modeled by the motion of a particle, right? You've seen those bears. Going like this, just like the snakes do. I don't know why a bear would do that, but there it is, okay? This is really just an excuse for us to throw a trig thing in here, okay? Really, that's all it is. So, can be modeled by the motion of a particle moving left and right along the x-axis according to the acceleration equation. These are like the quick calculations you can do in your head when you're stuck in the tree and the bear's like, coming after you kind of thing, okay? A of t equals negative sine of t plus 1/3. The bear's velocity is 1 foot per second when t equals 0. Find the velocity equation. Okay, so given what we know here, okay, if we want to find the velocity equation, what should we do? Integrate the acceleration, right? So v of t is going to equal the integral of negative sine of t plus 1/3 with respect to t. What is the integral of negative sine? Cosine. Cos t. Integral of 1/3, 1/3 t. And don't forget your plus c there, okay? All right. We need to figure out what that c value is, though. We want to find our particular solution here. What do we know about our velocity? 1 when t is 0. So that means, well, let's see here. We're going to plug 1 equals cosine of 0. All right. Here's your big chance, folks, from earlier. Cosine of 0 is 1. All right. And so c is 0. Okay, we're learning. Yay. All right, so cosine of t, v of t equals cosine t plus 1/3 t, and that's your velocity, because c is 0. Okay. What is the speed of the bear when t is 7? How do we find the speed? 7 goes into the velocity, and you take the absolute value. Okay, so speed at 7 equals v of 7 with the absolute values there. So it's going to be cosine of 7 plus 1/3, bless you, times 7, and it's the absolute value of that. Do we need to evaluate any further if this is a free response question? No. Remember, even trigonometry does not need to be evaluated. Okay, so we can just say that's our answer, and we'll put it in terms of what units? Feet per second. Okay. I have to be careful now because in my geometry class, I'm now doing trigonometry, and of course they use degrees, so I have to switch my calculators back and forth. So, math teacher struggles, right? All right, 0.87 feet per second. All right, last one. In what direction is the bear traveling when t equals 5? What determines the direction of motion of an object? Velocity. So we want to find v of 5. Okay, so this time we really do need to type this in because we need to find whether it's what? Positive or negative, yeah. Actually, you know what? Never mind. I apologize. We don't need to know this. 5/3, okay? 5/3, that's more than 1, right? And what's the highest value that cosine could ever be? 1, right? Cosine of whatever, the highest it can be is 1. So you're taking something that's got to be at most positive 1. You're going to add, or sorry, at least negative 1. So the lowest it can be is negative 1. The highest it can be is 1. And you're going to add something that's more than 1 to it. So it's got to be positive, right? This has got to be positive. We don't even need a calculator for this. Okay, so it's got to be positive, which means the bear is moving in which direction?
To the right.
To the right. Okay, the bear is moving to the right since v of 5 is greater than 0. Okay. So while you're in the tree, you can predict, the bear is going to be turning now. So you can see it.
You're like setting up in the tree. You're like,
All right, that's it, folks. You have the rest of the time for you to work on your homework or the problem set. Oh, you have a question? Sure, yep. Sorry. It should be posted already to Google Classroom.
actually, we didn't even decide whether they change the directions. We're just determining the direction.